Hi, everyone. I'm Rod Dayrit, Global Director of Business Development at Delta Q Technologies, which is part of the Zappi Group. I'd like to welcome you to this session. Please remember that this session is being recorded and it will be available on demand following the session. If you have any questions during the session, please add them to the Q&A tab, which is located on the top right of your screen. Note that the questions will be sent privately, but if there's an opportunity to interject during the presentation, we will do so. With that, I would like to introduce our speaker. I'd like to welcome Ben Waters, CEO of WiBotic, who will be speaking about wireless power technology, a topic that is popping up regularly in our industry. Thanks for being here today. Ben, looking forward to your presentation.
Thanks for the introduction, and thanks to the Zappi Group for hosting me here. Like Rod said, I'm the CEO of WiBotic, a company based here in Seattle, Washington, and that's where I'm calling in from today. And I'll be talking about wireless charging, but particularly about how it applies to autonomous systems and some of the differences that autonomous systems and robotics have to some of the traditional industrial battery-powered vehicles that need charging. But first, I'm going to start with a fun little analogy and some background on myself. So I'm a big sports fan. I played ice hockey growing up, and this picture is a picture of the team I played on in college. It was a club team, and we only had 8 players on our team. And if you know hockey, that's a very small team. Usually there's like 25 people on a hockey team. But we were 8, and I didn't really appreciate it at the time, but we had an incredible coach. He managed the 8 of us so that we didn't get too tired. We were successful. We were happy. We were a fun group. And for me personally, coaching and leadership and automation have some things in common. So I hope that by the end of this talk, you'll understand a little bit more about what I mean. But the spoiler is that, great coaches, leaders, and infrastructure, particularly charging for autonomous systems infrastructure, when things are working well, they go unnoticed, and that's just fine. So this is kind of going to be the overarching theme to what I talk about a little bit here as we get into automation and wireless power. So as many of you probably know, automation is becoming a big thing in industrial applications. There's a lot of macroeconomics leading to this, labor challenges, electrification, sustainability, energy efficiency, cost, and automation is one of the ways that a lot of businesses are looking to solve some of these challenges. And most autonomous systems are all going to require 4 main ingredients: power, data, sensing, and the ability to manage the fleet. I'm mostly going to be talking about the power and data side in this talk today, but certainly these are the trends driving automation. And as a result of that, there are many, many different types of systems on the rise for automation. There are drones, there are robots in the warehouse, there are robots in restaurants and underwater and on the moon, soon to be on the moon. But with all of these different vehicles, and with this being an emerging industry, there are many key challenges. For example, how do end users deal with charging different types of batteries? I would say that unlike perhaps more established markets such as forklifts and pallet jacks and large industrial vehicles, the battery spectrum of automation is like the Wild West. Companies are usually quick to choose which battery they're going to use. It's usually driven by cost and getting the size and voltage that you need. not so much considering, some of the long-term pros and cons of having made that selection. So for now, the batteries are all over the place, right? A lot of lithium iron phosphate, a lot of lithium ion, still some lead acid, but many voltages, many amp hours. Some have good BMS systems, some don't. So how is this effectively managed ultimately by the end users or the facilities that are using these robots and these autonomous systems? Another challenge is, how do systems operate in challenging environments? Even indoor warehouses are dusty and dirty and I would say a challenging environment. Of course, outside in the cold where robots and drones are being used to inspect power lines, out in the desert where robots are being used to inspect solar fields, agriculture applications, space applications. One of the particular challenges that is less so related to charging, but more so related to the data side is how, robots, I'll use drone as an example, right? A drone on a single flight can generate a lot of data. If it's got a high resolution camera, an infrared camera, it can generate, 30 gigabytes of data easily in a 30-minute flight. So now you have all this data that's way out in the middle of nowhere, and how do you get it back? So a lot of companies are struggling and trying to figure this out, right? Because if you're relying on the upload rate of LTE, for example, good luck offloading 30 gigabytes with a poor, LTE signal out in the middle of nowhere. So, some of these things are they're learning as they go, right? Automation is getting these systems out there. They're learning about these challenges. And I kind of view it as the responsibility of the infrastructure players in this field to help solve some of these problems, right? Robotics isn't going to be successful if one company has to solve all of these problems. There needs to be partnership and ecosystem cooperation to solve some of these environment and deployment challenges. The way that we look at it at WiBotic is these are the problems that we want to try to be solving. We think about the power problem, and we think about the data problem, and we think that they are related, and we think that infrastructure needs common hardware and software to be able to solve these problems effectively. So with that as sort of the scope of the industry and the challenges that I'll talk, I wanted to just share a couple videos that I think are very simple, but they highlight a couple of important differences when it comes to wireless charging for manual devices versus autonomous devices. So this is a video of my cell phone on a little wireless charging pad that's just branded WiBotic. And as you can see, when I first put the phone on the pad, I didn't have it aligned right. And then I made just a subtle adjustment until I saw with my eyes that the phone says, okay, it's charging now. We've all probably done this 100 times or more in our lives, whether it's with a wireless charging pad or plugging in a cable, right? The human provides the intuition for ensuring that the device is charging. But there's a lot of mental computation that we all take for granted that's actually happening there, right? I put it on, I waited a second, I saw that the phone was telling me it wasn't charging. I've had experience with this before and playing with getting it in the right spot. So I knew already that I just need to maybe center it a little bit better. And then I waited another second, and then the phone told me it was charging. And then I left and I went on with my day, and I expect that when I come back, the thing's going to be fully charged. There's a lot of intuition that the human's providing in this example. So let's compare that to a robot. So this video is showing a robot charging up against a WiBotic charging dock. the robot has sensors, it has cameras, it is autonomously navigating and making lots of minute adjustments to get in range of the dock. And now it thinks it's in range, and it's still making a couple of little adjustments. And now the blue light is on and it is successfully charging. But think about this now. So what happens if the robot drives up and with all of its navigational sensors and everything, it thinks it's in the right position, but it's actually not? You know, how long does it wait before it tries to dock again? What type of information is getting passed to the robot from the charging station to say that it's not docked properly, right? So this I think, you know, points out an important point that I want to make, which is autonomous systems require all of that intuition that we as humans take for granted when we're charging our devices, because we can just see what's happening and solve the problem and be creative. But all of that needs to be baked in, and all of those edge cases are where all the problems happen, right? If a robot did not have the ability to figure out all of those things, if it wasn't in the right position, this is a big challenge, because now it's just going to sit there until perhaps the battery dies and someone's going to have to go out and fix it, right? So all these edge cases come up, and with wireless charging specifically, they're made more difficult, because when you have contacts, for example, or a plug, right, you have instantaneous feedback that, okay, my device is hitting this contact and I'm seeing voltage and I'm charging. But with wireless, you don't have that until the wireless system starts up, and maybe the wireless system isn't going to start up until the device is in the right spot. So this is an important point. And I think, you know, all of these challenges are challenges that require a variety of factors. So the way we look at it at WiBotic, and I think the way anyone should be looking at it, is there's three main ingredients for reliable autonomous charging, autonomous being the key word. Of course, safety, and I'll talk a little bit about safety, communication, right? The feedback between the charger and the robot. If the robot's having to figure out all of those things on its own with sensors, maybe it needs more sensors than it actually needs if it was just communicating with the charger, and that adds cost and more points of failure. And intelligence, right? What is the best way to charge autonomous systems? A lot of it depends on the use case. Is it always needed to charge fast? How does that balance with the cost over time of having to replace batteries and deal with infrastructure for, you know, you've got 1,000 charging stations in a warehouse and they're all consuming a lot of power at the same time. Are you going to be tripping circuit breakers? You know, the robotics industry is learning all of these things that I think more traditional industries have learned the hard way and have standards for, but that's still evolving in automation. So I'm going to talk a little bit about each of these key points and then dive deep into some of the wireless charging things now. So a lot of companies that get started in robotics and automation tend to use a contact-based charging system because it's simpler, right? You know, and you can buy some contacts and you can buy a power supply and you can put some things together and the robot can drive up and charge. One of the big challenges that I think was unexpected is that when you're relying on a contact, as shown here, is a great connector. We use them all the time, Anderson power pole connector. But when you rely on a connector like this for autonomous docking, you now have this big heavy robot coming in. And even if there's a nice little funnel for it, it's going to be providing a lot of force on those contacts. So these contacts are typically rated for like 5,000 or 10,000 mating cycles. But this is a picture of one after 700 cycles because a robot was, you know, not so gently slamming into it all the time. The plastic shroud broke, the metal notches had been bent. And this exact problem has created fires in warehouses with robots that have used contact-based chargers. That has already been something this industry has experienced. If you look at it from a different way, you can do it with contacts. This is a picture of a Roomba, and Roombas have mechanical pins that hit little spring-loaded contact points on the dock. But if you look at that even in the home, or considering that for an outdoor or even a warehouse application, you've got dust, you've got maintenance, you've got issues to deal with that perhaps, unlike a system where it could just retry to dock, it might never make a successful dock if those contacts became damaged to a sufficient level. So a lot of these, I think, are the main reasons that companies have started looking more towards wireless solutions. You just don't have these issues with wireless. You introduce some of the complexities I showed in the previous video, but a lot of those things I think are getting worked out by the infrastructure. So I'm going to transition here and talk a little bit about wireless power. And can't mention wireless power without some of the original work that went on. And I think it's interesting kind of looking back on history at what started work in wireless charging, where it led to early adoptance, and now where it is today. So where it is today is there are standards for consumer applications, and it's pretty much in every cell phone now. And it's great. You can drop your phone on a pad in your car or wherever, and it charges. There's an ongoing standard for wireless charging for EVs, which is great because automotive manufacturers can integrate charging equipment into the car, parking lots, garages, perhaps roads one day can have systems that will charge the different cars. So there's a ton of work ongoing in this field now. And even beyond that, there are many, many different types of wireless power systems. For this talk, I'm going to be mostly talking about near field, inductive, and resonant wireless charging. But there are technologies out there that are being used for beam forming, using a far field or more of the electric field to transfer power over longer distances. It would be nice if there was once a day where your phone could just magically charge in your pocket. You never actually had to charge it, right? But there's some technology and regulatory challenges, and we'll see if that plays out. There's optical and laser systems. There have been demonstrations from companies who are harvesting solar energy in space and beaming it back to Earth with extremely efficient and extremely powerful lasers. So many different ways you can do wireless charging. Many of you have probably heard these terms inductive and resonant charging before. And ultimately, they're very similar. The physics behind them are essentially the same. It's the concept of generating magnetic fields and transferring power over short distances, but with very high efficiency. Kind of a fun example, back in the 1980s, this was almost right around the same time as electric toothbrushes, maybe even a little before. But there were corporations building inductive charging systems that were called TETs, transcutaneous energy transfer systems, to wirelessly power implanted medical devices like this artificial heart pump for patients who had end-stage heart failure. They were inductive systems. They used a relatively low frequency. The distance was very limited. Essentially, the primary coil was an adhesive that mounted to your torso and powered an implanted coil that was basically directly beneath the skin behind it. It was very heavy. It would get very hot if the coils were misaligned. And ultimately, this technology was not the technology chosen to power implanted medical devices. There were enough side effects with it, even though this was advantageous from not having to have a cable stick through the patient's stomach. But that is ultimately what this technology opted to do. So for patients with end-stage heart failure that require a ventricular assist device, which is what this is called, there's a cable that sticks out from the patient's stomach and connects to externally worn batteries. Perhaps one day wireless will make a comeback. But this was exactly the topic of my research. I was a PhD student at the University of Washington, and this was my PhD work. We were trying to revive some of that work with resonant charging and achieve higher efficiency, achieve more positional flexibility so that, the transmit coil didn't need to be an adhesive. It could be more worn on a piece of clothing and be less massive on the implant side. So this is ultimately some of the work that got me into wireless charging. And when I graduated in 2015, we founded WiBotic, although we chose to go down the route of automation and robotics instead of medical devices. So to dive into the technology a little bit here, there's many ways you can describe how wireless power works. I like using this transformer analogy. So if you go back to Physics 101, you will maybe remember that in a transformer, to deliver maximum power transfer from a primary winding to a secondary winding, you need to have your primary impedance matched to your source. The functions of the turn. So, in general, in physics, they say the primary impedance is 50 ohms, the source impedance is 50 ohms, your turn ratio is 1-to-1, and you have maximum power transfer delivered through a transformer. A wireless power system is essentially an air core transformer, where you have a transmit coil, a receive coil, and you can transfer power between them. There's many ways you can build the coils and build the amplifiers to have different improvement in efficiency and range and all these things. But I always like to come back to the impedance matching analogy, because in a wireless power system, the impedances are changing. We don't have this luxury of you have a fixed impedance and you can just match the impedance one time and then it's done. For example, the load impedance, if you're charging a battery, right? A battery is going to go through a cycle where it's charging with high current and constant current mode and then reach a point where the current level is very low. That's an example of the load impedance changing beyond what we can control, right? That happens. When you are looking at the impedance into a near field set of coils or an air core transformer, as the distance between the coils changes, that presents a very different impedance. Coils can look like a short circuit if they're close, and they can look like an open circuit if they're far away, and everything in between. And so what that means is that if we think about this, we want to have matched impedances. In order for the impedances to remain matched and to achieve efficient power transfer across changing distances or across different battery load power levels, there needs to be some way to account for this. If you don't do that, that means your wireless system will work at one very particular distance and one very particular power level. So to overcome that problem, one way to do it, and I'll talk a little bit more about it, is with active impedance matching circuits. So WiBotic and a lot of the research I did in grad school is looking at, you put these dynamic impedance matching networks and you can change them on the fly and kind of counteract the impedance changes that are happening naturally in the system. Now, even with this, there's a lot of ways you can do it. One way is with frequency tracking. And this is one way that a lot of systems today use. The tricky part about using frequency tracking at higher frequencies is the bandwidth that you need to tune your frequency to would violate the allowable bandwidth that the FCC and other regulatory bodies of the world allow. So what this plot is showing on the near axis is distance between the transmit antenna and the receive antenna. On the y-axis is the operating frequency, and the z-axis is a metric of efficiency for the wireless power system. So you can see that if you could tune the frequency and ride that ridge as the distance is changing, you can achieve constant efficiency. So the efficiency would not change even as the distance between the coils is increasing. Right? This is kind of counterintuitive to what we often think about wireless systems, which is as you get farther away, the efficiency goes down. But what this is showing for near field wireless power systems is that's not necessarily true if you can ride that ridge and tune the frequency. And eventually you'll get far enough away where the magnetic fields and the coupling just aren't sufficient enough, and you'll have a quadratic decrease in efficiency at some point. So this would be great, but again, you violate the bandwidth that you can operate at depending on the frequency range that you're using for your wireless power system. So what we did is, going back to the active impedance matching, this is that same plot, but now those active impedance matching banks are doing work as the distance is changing. And that creates this nice flat ridge that is coinciding with just one operating frequency and allows for a very flat efficiency curve across a much wider range of antenna. So again, there's a lot of ways, there's a lot of antenna design work, there's a lot of amplifier, there's a lot of frequency selection that works. This is just, kind of one example of how you can achieve more flexibility in a wireless system. And this is the method generally that we employ at WiBotic. And I'll show just a video here that kind of highlights what this means and how this works. So in this video, the dynamic tuning is disabled, and you can see there's really only one position where the 60-watt light bulb turns on. This is a video from my grad school days that I like to show. So now you'll see that the dynamic tuning is enabled, and the bulb is able to stay powered across a much wider operating range, even if the load is moving dynamically, which a robot typically isn't going to be doing, but if it needed to, the system could overcome that. And that's an important point, right? We emphasize the flexibility at WiBotic because, going back to that video of the robot docking, even though they have great sensors and everything, when it comes to autonomous docking, there's always going to be edge cases where it's a little bit off. And if it's a little bit off, and that means it needs to go through and reattempt a dock, and that adds 30 seconds to that one charge cycle, well, multiply that by thousands of robots and thousands of charge cycles, and that substantially adds a lot of downtime, which is very bad in robotics, right? Robotics are trying to be more productive and make things more efficient, and downtime is bad. Going back to the key challenges, I'm going to transition and talk a little bit more about the second challenge, which is communication between the charger and the robot, or the autonomous system. I'm sure many of you know this, but generally this is what a typical charge and discharge curve looks like as a function of voltage and time. And in order to calculate state of charge accurately, right, a good BMS will do this well, but in robotics and automation, there aren't always good BMSs in the loop. You essentially need to be computing the energy over time, right? And there's a lot of added complexity for an autonomous system because the robot has an active hotel load. It is consuming power to keep its sensors on and its wheel motor controllers engaged. And that load isn't super consistent. So it makes it difficult for both the charger to know, okay, when is this battery actually fully charged? Because I've got, 4 amps going to the robot and 6 amps going to the battery, but those kind of bounce around, and it's difficult to always know if you're not communicating between the robot and the charger. And it's equally hard for the robot to know, is the charging done? Some robots don't even have a great state of charge calculation. They're relying on voltage. And as we all know, voltage can fluctuate with temperature and time and battery health and all these things, and isn't a great way to assume if your robot has 20% left or if it's actually 0%. And another challenge in robotics is with temperature and age, right? As the battery ages, you can think about, I like to think about drones as an example here, right? If a drone's going to be doing 10 flights a day and be pretty hard on the battery, right? Heavy discharge, they want to charge fast. You reach 1,000 charge cycles very quickly if it's truly an autonomous drone doing a lot of flights a day. And if that drone doesn't have a really good awareness of its state of charge, it might think it's got 20% left. And on day one, that meant it's got 2 minutes of flight time left. But on day 50, it's only got 30 seconds of flight time left. That's a huge problem, right? So these things and these communication challenges are an important part of the evolving standards and the evolving, in my opinion, collaboration that's really essential between all of the infrastructure providers and the manufacturers of the vehicles themselves. So the one way that we've looked at it is, trying to make open and easy to use and non-proprietary communication protocols, right? Follow what has worked in the past. Make sure that the charger can expose the parameters it needs. Make sure that the robot and the battery are able to expose the parameters for state of charge, health, airs, all of those things, so that the robot can make informed decisions about, what it needs to do to operate safely and efficiently. So the final topic is on the intelligence. And I alluded to this earlier, but we get asked this question a lot. And the answer, of course, is it usually depends. But what is the best way to charge? Is it good to charge fast all the time? How do we maintain a high level of uptime, right? We will hear, we have 10 robots deployed, and no matter what we try to do, there's always a time where all the robots need to go charge at once, and then none of them are available. Like, these are tricky questions to ask. Do you always charge to 100%, or is it better to charge to 80%? So I wanted to share kind of a cool video that we've worked on some simulation tools at WiBotic to really understand this problem. So what you're seeing in this video is a simulation of 100 robots, the orange things moving around, and 50 charging stations, which are the green sections on the side. And in this tool, you can change the number of robots, you can change the number of charging stations, and we make some simple assumptions about charging time and energy consumption of the batteries. So those aren't being modeled perfectly, but we have some assumptions that we make about that. And then you can see what happens, right? How does that affect the uptime of the vehicles? How does that affect the charging power? What is the maximum charging power if you had all robots, charging at once? And is that going to pose issues for the building that has to manage, grid level power, making sure they're not going to be tripping circuit breakers and doing all these things, right? These are, I would say that very few companies in automation have had to deal with the pain points of not doing this well. But I think if we learn from industries that have all had to sort these things out, building level backup power, forklifts, like all of these industries have experienced these things, and robotics is going to inevitably as it grows. So this tool led us to a couple of interesting or maybe obvious conclusions. Number one, I should caveat this is for lithium batteries. Number one, charging fast does diminish the overall longevity of the battery. And so where possible, try not to be charging above 2C for most of the packs. Certainly maintaining charge between 30 to 70% has a pretty substantial increase in the uptime of the fleet, because when you do this, You avoid those constant voltage times that aren't as efficient with putting energy into the pack. But you also increase the availability of the charging stations. So if the goal is to decrease the total cost of how you operate a fleet, it'd be nice to have as few robots and as few charging stations as the end customer needs, because that's going to be the most cost effective. Opportunity charging and minimizing the distance traveled to charging locations, right? If the robot has to drive all the way from one side of a facility to the other to reach the charging station, yeah, it's only a couple minutes, but multiply that by all the robots and all the times it has to do that, and it adds up really quickly. So thinking about station placement, thinking about really being smart with fleet management about when to go charge, right? Do you only go charge when the battery reaches 20%, or do you charge opportunistically? And really think about, okay, I could do a task, or this other robot could do a task. There's a charging station right there. I'm at 40%, that robot's at 70%. Most systems are not making these level of decisions yet. Charging is often sort of the last thing companies deal with, but then it becomes an important thing because, batteries die if it's not done well. So those are just some of the interesting things that we've learned. And I wanted to just share one example of how it relates to cost. And this has already snuck up on a lot of companies in robotics. This is a very simple model, but if you assume that to replace a battery on a robot, right? Eventually the battery is going to need to be replaced. You have to buy a new battery. You have to, in most cases, ship the robot because the batteries aren't really intended to be swapped in most robots. Most robot companies are leasing robots, and the batteries are like really integrated into the robot. So that robot's getting put on a pallet, shipped back, batteries getting replaced, and then you have to factor in the downtime or supplanting that factory with a backup robot or a new robot. So that cost, I think, can even be higher than this if you have, heavy stuff and shipping internationally. But generally, that's what it looks like. And if you multiply that by 1,000 for 1,000 vehicles in a fleet, what we're trying to point out here is if you can just increase battery life or increase uptime or really any of those parameters that I talked about before by even 20%, it's a substantial cost savings. And I think these dollar values and these numbers are only going to increase as there's more and more robots out there. And it's going to force companies to really think about this level of optimization. And the infrastructure players, in my opinion, have a duty to, be thinking about these things today. So those are kind of some of the technical summaries on, just what we've learned from the infrastructure and charging side of automation. And I'll talk for the last couple minutes just about some of the industries and applications that we see a lot of growth in. So in automation, there's certainly more applications than these four, but these four seem to us to be the ones that are growing fairly quickly. Warehouse automation driven by growth in e-commerce, manufacturing, material handling, robots in manufacturing plants carrying goods around, working alongside people and doing the things that are difficult or people aren't productive at doing. Safety and inspection, right? Monitoring cellular infrastructure, monitoring power line infrastructure with both robots and drones are an industry that we see a lot of growth in. Retail, right? Retail doesn't necessarily just mean grocery stores, but restaurants, especially in Asia, retail robots and service robots are arguably, the biggest industry. Whereas in the US, it's probably more heavily on warehouse and manufacturing. But all of these industries are I think, doing those three things I mentioned earlier fairly well, right? They're on their third and fourth generation of robot or platform. they're optimizing things. They're not just getting things to work and deploying pilots. That to me is a sign that the market's really maturing, and there's opportunity for the infrastructure providers to grow into these markets as well. I'll talk just a little bit about WiBotic here. WiBotic provides autonomous charging and data management solutions for autonomous fleets. We work with a lot of mobile robot manufacturers. We work with some end customers who are using multiple robots from different vendors, and they want common infrastructure because they've learned or experienced some of these cost or reliability pain points. And we have software that does a lot of the coordinating charging across your fleet, right? Our goal with the software is basically to just give as much data as possible to the robot operators and allow them to make smart decisions. And in some cases, maybe you need to prioritize uptime and all you want to do is charge fast. In other cases, maybe you have a night shift where there's not a lot of activity, and you can optimize your cost and optimize for battery longevity and do some updates or maintenance during those downtimes, the natural downtimes. From a hardware standpoint, we're not unique here. Most wireless solutions out there will typically have 4 components. There's a transmitter and a transmit antenna. Those 2 components comprise the docking station, and there's a receiver and a receiver antenna, and we call the receiver the onboard charger, because in our system, the onboard charger is a programmable battery charger that can charge any battery between 0 to 60 volts, up to a kilowatt, up to about 36 amps max is our highest power charger today. And it can be programmatically adjusted. So if there's a lithium battery on one robot and a lead acid battery on another robot, those 2 robots can still go charge from the same charging station because all the charge control is taking place on that onboard charger. The software manages those things I mentioned, but the data piece is something that we do as well. And the way we do the data piece is we have a CAN API that allows for the onboard charger to communicate with the robot or vehicle, and the robot can write its own data back to the onboard charger. And then we have a data link between the WiBotic transmitter and the WiBotic onboard charger in which that data can be accessed. So generally where we see this as a very useful feature is in a warehouse or in that remote power line example where data might be unavailable. Wi-Fi drops out, radios get crowded. So if the robot normally has that mode of communicating its data out, but for whatever reason, if that mode of communication is unavailable, the robot, instead of just being stuck in the middle of the warehouse without knowing what to do because it can't receive an instruction, it can know to go back to the charging station, reestablish a data link, and move on from there. So whether it's used as a redundant link or the primary link, we kind of look at this as like, okay, there's charging infrastructure out there. What else can it solve? What can we do to help this industry avoid having robots get stuck? And that is bad for everybody because it's going to inhibit the adoption and the growth for that end customer. So those are just a few things about what we do at WiBotic. It's an exciting time to be in this industry because I feel like automation really is solving these problems of adding new capabilities, allowing end customers to finally realize cost savings after all of the investment that they've made into automation. And the cool thing I think is, a lot of robots that are successful today aren't necessarily replacing people, right? They're working alongside people. People are still needed to do a lot of things, but the robots help them do the things that they don't want to do and do the things that the business needs to do with higher productivity and better efficiency. This is really where robotics are excelling today, and I'm sure there will be more growth in this industry in the future. And to conclude, going back to my analogy of, when things are working well, they go unnoticed, right? I think robots need to embrace more of this mentality. They're very noticeable when you go into a warehouse or when you go into an industry using them. And that's okay, right? They should be noticeable because people think they're cool. They shouldn't be noticeable because they're clunky and they're slow. And if you step in front of it, it doesn't know what to do, or it struggles to get onto the charging dock and charge properly, and it's beeping at you that it's got a low battery, right? Those are the areas where I think robots can learn from great sports coaches and great leaders. And to work well, you need to go unnoticed. So thank you again. Happy to answer any questions. And there's my contact info.
Ben, appreciate the very useful and insightful presentation from WiBotics. Again, I'd like to remind the audience, if you have any questions, please use the Q&A tab to the top right. There is a question, but I'll start it off. You talked about some of the challenges in the industry. You summarized your presentation about when things are working, some new innovations kind of go unnoticed. And you also talked about some of the technology innovations that you guys have implemented in WiBotics itself. Where do you see wireless power transfer's evolution going in the future now that autonomy and automation is becoming more prevalent because of manual labor shortages, costs involved, and whatnot? Well, I guess, I'll let you address that first.
Yeah, no, it's a good question. And I think, the industries that are going to be adopting wireless charging, I'll talk mostly from, an industrial perspective first, right, are the ones that have harsh environments where, contact-based charging is just kind of obviously not going to work, right? Outdoor applications, for example, warehouse applications where they really need to be running at a high level of uptime, and maintenance or having to change contacts is extremely problematic. I think those have been the industries that we've seen adopt wireless charging first. I would say that it's still not at the point where it's the first thing that most robot companies think about. I think that will change as it becomes more broadly adopted, because I really do think, if the efficiency is almost on par with contact charging, if contact charging is something that generally that's like, there's not many like vendors of like, here's a contact charging solution that just, right. That's more of like, they integrate contacts, they integrate power supplies. They're more doing that themselves. So, I think those will be the factors that kind of drive it to become more of the obvious first choice. But if companies go down that route of, okay, we're going to build our own contact system, they may experience some of the pain points I mentioned. Mm-hmm. And they may get to the point where they're like, all right, we don't want to be charging experts, right? We got certifications to deal with. We have to go through all these certifications for our contact system. Should we just buy an off-the-shelf wireless system? Yeah, we still have to do some integration with, but that's kind of just a module that we can throw into our robot. So I think it's getting there. But I think the outdoor applications are where it's heavily used today. The indoor applications are migrating more towards it. I think a lot of the myths of wireless charging being really inefficient or really expensive, no doubt they're slightly less efficient and slightly more expensive today. But, companies like WiBotic and many other companies trying to, be successful building wireless solutions in this industry today are working hard on that stuff. But we also need the volume to, help do some of that, right? So some of that goes hand in hand. Yeah.
Good. Appreciate the response. I know there's still the challenges ahead and really aligning in the respective markets that have the most benefit for this. But it's good to hear your perspective on this. We do have a question that came in from Marco Panzeri. It says, considering the closed loop control necessary during recharging cycles, is the wireless charge not applicable on a manual electric forklift? You talked about industrial applications. And then to follow that up, the question is, do you see any chance to serve vehicles not autonomous, right? And then I guess there's a follow-up question from that is cost versus improvements in that case, or benefits.
Yeah, no, thank you for that question. And I acknowledge that the majority of my talk was heavily focused on autonomous systems, but absolutely, wireless charging technology can be applied to non-autonomous battery-powered systems. And WiBotic specifically looks at those applications just as much as we look at autonomous applications. Just sort of the theme of my talk was more on autonomy for today. But I'll give one specific example of something. So if you look at this diagram, generally when we integrate an onboard charger with one of our partners for a more established vehicle, right? Let's take a forklift, for example. A forklift has pretty robust power distribution circuitry, battery monitoring circuitry. So a lot of the time when we are looking at vehicles like that, we are not assuming that we're going to, the onboard charger is going to be directly connected to the battery, which is another important, thing to think about. So it's not straightforward because right now, like the charger doesn't see the battery. Let's assume we're not communicating with the forklift at all, right? It's just a block of hardware that is expected to charge the battery without issue. So we have what we call a mode, we call it power supply mode, right? So the charger can still have a specific voltage limit that it can output, 24.2 volts, and a current limit that if exceeded will, just like a power supply, limit the current, and as a consequence, voltage would sag. But for a forklift application, for example, the current limit of the charger would be set higher than the expected current limit of the charging that particular battery. So for sure, there's a lot of ways that this system and really any wireless system could be looked at for non-autonomous devices. Generally, some of those things I mentioned about, you're not getting directly connected to the battery, or, there's not the opportunity to get designed into a vehicle from scratch. It's looking more like, okay, this vehicle already exists, and now we need to add this charger because we want wireless charging capability, but we can't sacrifice, designing a whole new forklift and having to start from scratch. So we do a lot of that at WiBotic, and we've had experience thinking about, those aftermarket integrations with non-autonomous devices. And there are some technical differences, like you pointed out in the question. But generally, the infrastructure is getting better. We have experience with these types of things just as much as the autonomous side when we're, designed in from the beginning. Great.
Appreciate the response there. It does shed some light that this is not really just suited for autonomous applications. There are some applications where wireless does have some benefits. So appreciate your feedback. The next question that came in are, so they are particularly interested in understanding if you test different technologies, recharging technologies of different battery types outside of just lithium? And if so, what are you doing in that space?
Yeah, it's a great question, and I think WiBotic's been around for 8 years, but we still feel like we haven't been around for that long, and so we have recently, really tried to engage with battery manufacturers directly. Right, I mentioned earlier that probably the majority of the batteries that we see in robotics are lithium iron phosphate. Lead acid, we are seeing more as we are looking at some of these, other types of vehicles, perhaps not robots. Yeah. And of course, there's different charging profiles for those different batteries. So within the confines of the WiBotic system, at least, you can select the battery chemistry. When you select lithium iron phosphate, for example, we have, safety limits that prevent the charger from, overcharging a battery. Mm-hmm. We will not charge if the voltage is below a certain threshold. There's provisions for which that can be overruled if the BMS, for example, is intended to cut the voltage off and the voltage is supposed to be low because the battery needs to be, recovered. But for example, when you select lead acid, right, we generally have the third stage of float charging. Mm-hmm. It can be time sequenced, the current and voltage limit for different, TPPL versus gel versus AG, right? There's slight differences in those voltages that are gonna be required for that third float stage, or some even require a pulsed stage. Mm-hmm. So, one of the nice things about the way we architected our system is a lot of that is for us firmware, right? Mm-hmm. Which may sound scary to a hardware heavy audience, but we put this through lots of paces, right? We have a partnership with a facility here at the University of Washington called the Clean Energy Institute that has battery cycling equipment. And we put our chargers on there, and we put it on there with batteries that we haven't encountered before. And we run it through thousands of charge cycles. And we share the data with the battery manufacturers. And, we want to make dang sure that we're not doing anything that's going to cause an issue at a, customer site, right? So we have a lot of ability to control that within our charging algorithms. And like I said before, we also have the ability to essentially turn that off and let it just be a power supply. So we as a company are very interested and open to, working with partners in the ecosystem of batteries and different battery types. And we also hope that the robotics community, consolidates a little bit more and kind of, whether there's a standard or not, picks fewer subsets of batteries to use.
Correct. Well, thank you for that. One last question. We have about just under a minute and a half left. The question is from Philip. Do you see a market for off-road vehicles, or is a charging infrastructure one of the obstacles here?
Yeah. Off-road vehicles, I'll assume means, more, large off-roading vehicles, or maybe I'll even include, EVs, right? So generally, I think the conception of wireless charging being slow and not applicable to big vehicles isn't really true, right? At the end of the day, it's just about power, and there are wireless charging systems out there today that do 150 kilowatts for charging electric buses. WiBotic specifically doesn't operate at those power levels, but it's not like wireless can't do it. So I think that from that perspective, certainly wireless charging can apply to those types of vehicles. And for off-road equipment that's going to be dirty and dusty, may be a great option, right? We work with a lot of robotic companies that build outdoor robots, and man, dust is a serious challenge. And I think it gets overlooked actually as to how big of a challenge it is in the robotics community today. But we have some experience with our chargers being, outdoors in the Arizona summer, for going on 4 years now. And then, similarly in the Chicago winters. And, should you even charge the battery if it's that hot outside or that cold outside, right? So we have temperature limiting built in. Ultimately, the customer, can kind of choose what they want to do. But we're not going to charge if it's above, 45 C ambient or if it's below 0 because, most batteries aren't going to want to accept that. So yeah, I think wireless is certainly something that those industries, there are technologies today that work at power levels for electric cars, that work at power levels for off-road vehicles. If you have interest in chatting more about any of that, certainly our team would be happy to chat. And we'll be pretty straight up with you if the power level we support wouldn't work for that application, but we can make some good recommendations.
Yeah, and that's definitely a good point. It's really just sizing your requirements to meet the technology needs for your application. But yeah, appreciate it, Ben. This was very informative. There's some good interaction with the audience. Again, if you need to reach Ben, on the screen right now, it's his LinkedIn. Way of contacting him is on the screen. So if you do need to reach out, just reach out to him via LinkedIn. So again, thank you, Ben. Appreciate it. And that would be the end of our session.